Hello, everyone. Welcome to our webinar, Streamlining Turbomachinery Design with Helix and CFturbo. My name is Lisandro Maders. I'm the head of sales and marketing at Engis, and I will be your host today. Before I start, everyone is listening to listen to me fine? Yeah? Okay. So the main objective of today's webinar is to showcase the seamless integration between Helix and CFturbo, developed collaboratively by Engis and CFturbo. And this integration includes a feature in CFturbo that exports all necessary information directly to Helix to run a high-fidelity CFD simulation by the use of automated scripts and best practices. And the result of this great collaboration is what we want to share with you today. Before we dive into the presentations, I would like to remind you that in case that you can submit your questions at any time using the Q&A feature, and we will address all your questions at the end of the session during our Q&A segment.
Good morning. Maybe I can quickly introduce myself. I'm with CFturbo since the very beginning, since 2008. I have currently the position of that of a senior scientist, and I'm basically responsible for the implementation of turbomachinery design theory into our CAD package, CFturbo. As I said, CFturbo was founded in 2008. At that time, it was not a complete new company, but a spin-off of an already existing engineering service company. In 2017, we founded a subsidiary in the United States in order to have our own kind of daughter that is serving the Northern American market. Currently, we are working in 3 different fields. One is that we talk about today, the development of the design software with everything what is necessary to this end. So it's not only the software itself, it's also the development of capabilities to have it integrated into automated workflows. And of course, we make customer development as well as training for the software. Secondly, we offer also engineering services, especially if people don't want to buy the software just because they don't need it often enough. And then we apply CFturbo for the geometry generation and CAE tools for validating the designs, and we make use of digital design space exploration and also automatic optimization. And the third thing we offer is the workflow development, because very often companies have a set of special CAE tools, and they want to set up, for instance, a design of experiment. And then we can help them by doing that and giving the proof that the workflow is running, and then implement it on their side, and then they can do some systematic investigations. We sell the software and the services worldwide, and we do that with local partners. And here you can see that where we are all located. The 2 yellow dots are those with own offices. This is just a set of clients we have currently. As you can see, we basically serve any kind of industry, because you can imagine that turbo machines are part of any technical system. So it can be really home appliance, but also rocket engine application, basically anything that you can think of. The software itself is a modular software, so you can design modules of a turbo machines, and modules can be impellers, vane stagers, and volutes. Meridional shapes can be centrifugal, mixed flow, and axial. And we offer special kind of implemented theories for pumps, fans, compressors, gas, and hydro turbines. The difference to a general purpose CAD package is that that we call it a conceptual design. So you always start with the operating point, and then we try to do a best point or best efficient point design, and we apply the solution of fundamental balance equations plus empirical correlations. We apply a full parametric geometry set, And we also consider the manufacturability, stress-related stuff, and something more. And you get a fully parametric 3D geometry, which then can be used, for instance, also in an automated optimization process. Here are given some examples, some pumps, actual pump, centrifugal pump, shrouded. Then in the lower left corner, there's a bowl diffuser pump, which I'm going to demo today. And also special pumps can be designed like that wastewater pump, where you have to have a certain clearance to allow dust to be transported. Designs can be multi-stage, as in this case, 3 stages, a 3-stage pump. Every stage can be individually designed, but it can also be a copy of just one stage in order to reduce the set of parameters. Blowers, it's actually the same. Again, there are special blowers, so like the squirrel cage blower here in the middle, or some special automotive cooling application fans. And this is the last example, is that of a contra-rotating fan, where one doesn't need vaned stators. Compressors, so there is a turbocharger compressor with splitter blades. Then there's a 2-stage axial compressor, a process compressor used for in the industry, and another industry compressor, which here is a 2-stage example. Gas turbines, it's similar, again, and a turbocharger turbine. And the last picture here shows an example how the geometry can be exported. It can be exported as a segment, which again allows a very efficient, for instance, validation in a FEA package, for instance. Some Francis turbine examples, and some examples on which features are implemented. So there's one very important feature, which is the reverse engineering feature. And with the help of that, you can quickly get legacy geometries into the parametric description in CFturbo. And maybe the last page I want to show is how we see CFturbo in the design process. So there is the geometry generated by CFturbo, and one wants to validate it quickly, and therefore we have implemented a set of interfaces, and those interfaces allow quick meshing and simulation, and the whole thing can be part of a workflow, of an automatic workflow, and that allows the automatic optimization. Okay, and my last page is just, I want those that travel to London next week, I want to invite them to our booth 616, because we are an exhibitor there. Okay, thank you for the time being.
Okay, so a few words about Engis. Our company is an independent CFD software provider. Company was founded in the UK in 2010, and our headquarters are still based in London, in the UK. I'm talking from our office in Italy, from Trieste, and we have several offices around the world, as you can see here from this map, and we rely on distributors in the Far East, for example, in other countries. Our products are namely Helix, with a set of add-ons for different applications, to the optimization, to the machinery and marine hydrodynamics, and finally Elements, vertical Helix for automotive applications. In terms of Helix, which is what is today for the demonstration, this is an open source based software which comes with a very easy to use graphical user interface, and open source core, which provides unlimited scalability, which means you can run an arbitrary number of simulations concurrently at no extra HPC license cost. And all our solvers and methods are validated and accurate based on a series of DMD and tests that we run. And since it's the open source, the code base open source, is fully transparent, so you can look inside the code and see how it's implemented, all the different models that are there. And we also provide commercial software, extensive written documentation in terms of tutorial, methodology, and guidelines, and so on. And we provide a technical support service to our clients. In terms of physical modeling, for today we're going to talk about rotating machinery, but we also deal with transient flows with moving dynamic meshes, but also multi-species, gas dispersion, pollutant dispersion, tracers, and so on. And typically also thermal simulations for a range of cases, multi-phase flows, both free surface flows and Euler, and Lagrangian as well, and finally high Mach number compressible flows. Okay, in terms of rotating machinery, we have first an automatic mesh generation and a set of tools for setting up a case and solving the solution, and finally a dedicated set of post-processing tools. Starting from the mesh generation, our mesher is next dominant meshing tool. It runs in parallel and produces high-quality meshes with detailed feature capturing, low Y plus, and no layer collapse. In terms of coupling to CADs, well, we deal with most of the CAD formats, and we also are able to import different meshes from outside, from third-party tools, and we have a set of tools for dealing with problematic geometries. When it comes to run rotating machinery components, you can either choose to run a full 360 model, for example, using an MRF, so a static mesh with a source, a momentum source to model the rotation of the impeller here, or you can run fully transient with a dynamic mesh motion, as shown here on the right. Otherwise, you can run a sector model in case of symmetry, like in this axial fan, or you can run a transient model using a dynamic mesh motion, as shown here. When you need to do post-process, you can access our turbo post functionality, and this allows you to create streamlines or span-wise turbo slices, meridional plots, like in this case, perform circumferential averaging, and finally also blade-to-blade plots, shown here. And finally, you can also plot 2D charts, for example, for blade loading, inlet to outlet, up to shroud. And today we are going to talk about our CFturbo to Helix interface that we developed together with the development team of CFturbo. And this is based on a Python API, which we provide in Helix. And this basically allows you to take the model created in a CFturbo and automatically create the mesh, set up, and run in a row using a specific sequence. And this is what we are going to talk today. Okay, so that was my last slide. So I will hand over to Oliver now for the live demo.
Thanks. Okay. Yeah, whenever you start a new design in CFturbo, you have to choose which kind of machine you want to design. Today's machine will be a pump, and that's why the central entry into that design will be the definition of the design point of that pump. So, and we together picked one with a certain volume flow of 210 cubic meter per hour. It should generate a head of 10 meters, and it should run on 2,900 RPMs. It's in every design step, it's the case that we give information that you can use for getting a feedback on what you have done so far, and also you can make use of it in order to get some empirical results based on this. So here, for instance, the specific speed is calculated once I change the focus, or we get the location of that operating point in the coordinate diagram, and from that you can immediately say what is roughly a good diameter for your at least single stage pump. And that's the case for every design step. what is also important, of course, is that you choose the correct fluid and with the correct fluid properties. To this end, we ship a couple of descriptions, but you can extend that by your own experience or by using either the open source library CoolProp, or if RevProp is installed on your computer, you can also use RevProp. Pick one of the fluids there, choose a typical reference temperature and pressure, and then you get the properties that should be used for the design. If the fluid you have chosen is described in both of these libraries, then you can also make use of the models that are used there. If it's an own defined fluid, it will be treated as a fluid with constant properties. Okay, once the global setup is defined, you can add a new component to the project, and the central component in a pump is, of course, the impeller, and that's why I'm going to add a centrifugal impeller. Centrifugal impeller means also you can define a mixed flow impeller. If you want to define an actual one, then you have to choose a different menu item here in that menu. Yeah. What you have to do for a component design is you have to run through a set of design steps. Every design step defines a unique design parameter, which means if you want to change that later on, you can only do that at one particular location in the process, and that's a precondition for being able to incorporate CFturbo in, for instance, a batch run into a DOE or an automatic optimization. Okay, so what I have to do is I have to go through those 6 design steps before design is finished. As I said before, we use the solution of balance equations as well as empirical knowledge. So here, for instance, I can use the work coefficient for a proposal for the impeller diameter, and all the empirical data, they are listed in what we call the approximation functions, together with the source where the data are taken from. In this case, it's from Johann Gülich's textbook. Based on these settings, we make proposals for the main dimensions. The main dimensions are just the 3 diameters and the outlet width. I can overwrite it at any time, and that's what I want to do, just to get rid of the decimal places and make the numbers round. And again, I get a feedback on where am I located in the coordinate diagram, where are how do the mid-span velocity triangles look like, and what are average values in the inlet and the outlet, and that's what I get just as information. Once this is done, I can go to the next design step, which is the meridional shape description. Here, the 3 diameters are the constraints. As I said before, you can only change them at one particular location, which was the first design step. If I would like to change them, I have to go back, but that wouldn't be a problem because everything is parametric. Here, I can change the actual extension. I can grab and drop the control points, but I can also directly set parameters. And the same applies for the hub and shroud contour. And what I also get as a feedback is some sort of a potential flow solution together with the streamlines based on the potential flow solution. They might be later on used for some other feedback functions. Okay, so everywhere in the design, it's worthwhile to right-click onto geometric entities because there might be some extra functions hidden there. And here, for instance, at the leading edge, I can tell what kind of edges should be straight or a Bezier curve and things like that. I'm going to leave it like that is. If I now press OK, in the meridional preview gives something familiar, and also the 3D view gives also 3D geometry. The next design step is to tell what is the general shape of the blade, what's the number of spans I would like to design the blade on, what's the number of blades, and what are leading and trailing edge angles. Again, we make proposals if we are in the automatic mode or if we press the calculate button. And again, then we apply empirical knowledge, like, for instance, the slip model for the trailing edge and the Euler equation for the calculation of the trailing edge angles. Once I'm happy with that, I can go directly to the next design step, which is the mean line design step, where skeleton lines can be defined that make up the blades with a so far zero thickness. So what I can change here is, for instance, the rep angle, again, by changing control points, but I could also directly type in rep angle and make a direct change with a certain digit. Again, I get a lot of feedbacks, which I also can customize on the right-hand side. So, for instance, the lean angle distribution, or an estimate on relative velocity distribution, and I could change control points and watch how the acceleration and deceleration will change in that relative velocity diagram. If I press OK, then in 3D, I have now blades with zero thickness. Thickness values can be added in the next design step, either in a linear way, like here, but also in a kind of profile way, where some control points, again, busy point-based, can apply the thickness, and you see it here, how it's going to look like in the 3D preview. The very last design step is how to shape leading and trailing edge. The default is an elliptic shape for the leading edge with a certain radii ratio, and a trimmed trailing edge trimmed with the impeller diameter. And I'm going to leave everything on default because I just want to show you in principle how a design would be done. What I also like to add is some hub and shroud contours, which can be done here in the meridional design step again. So I can set an initial offset here for instance, 2.5 millimeters, and I can give him a certain contour at the hub, just by, again, what I said earlier, splitting curves, setting them. There is a snapping feature so that it's easy to generate any kind of rotationally symmetric curve. And I can also increase the degree of the curve, and that would allow to have for instance, a Bezier curve here also at the hub. Finally, once I want to have the impeller finished, I can apply fillet radii at hub and shroud. If I run that, then it takes a couple of seconds, and in 3D we will then see a material solid, as we call it. And once it's finished, I can also show some more information we can get from that. So here we have the material solids. You see the fillets and the hub and shroud material contour. If I go in the component tree on the solid, I can output some more information that might be useful. So for instance, with a certain density, I get the mass of it. More interesting is probably the moments of inertia, because those values can be used early in the design process for instance, dimensioning the bearing system also. I want to finish that stage design, and by doing so, I'm going to add a diffuser that should do two things. It should bring the the flow back to the diameter of the inlet diameter of the impeller, and it should reduce the swirl in the best case down to 0. And to this end, I'm going to add a bowl diffuser type with blades, of course. Again, main dimensions will be the first step, so the location of the inlet hub and shroud point and the outlet hub and shroud point. The next step is very similar to the impeller design, is the meridional contour design. Again, we have a preset, a predefined default setting of the control points. That's why we immediately see something at least familiar. Again, I can adjust this by right-click and getting access to other features. So, for instance, I want to have it horizontal at the outlet. So I'm going to add a 0 angle here. I want to have the leading edge convex rather than concave, and that's why I'm going to change that here a bit, and maybe changing also the hub contour a bit and giving him a smoother cross-section distribution. Again, we have this potential flow solution here. And again, we get, after every change of the design, we get an updated flow solution. And that's, of course, only possible because it's potential flow in 2 dimensions. Okay, very simple, similar to the impeller. The next design step is to tell what is the general shape of the blade, what is the number of spans I want to use in the design process, what is the number of blades I want to use, and that can also be chosen with respect to, for instance, some interferences that might happen between impeller and stator blades. And to this end, again, the default is given in order to have, for instance, a lower noise level. Okay, and finally, we can make proposals for the leading edge because we have an estimate on what does the swirl look like that is coming from the impeller. And if we want to have a 0 incidence leading edge, then we can make a proposal for it. At the trailing edge, it's a bit different because we do not know what is the swirl that should be left in the flow, and that's why the default is 90 degrees. But one might, compensate again for some slip losses either by clicking by telling more than 90 degrees, or either by defining a deviation angle directly, and then it would be initially different from 90. Okay, so that's again like it was in the impeller. The next design step is again the mean line design step. Initially, the rep angle might be a bit too big, so again I can take it down at the hub and the shroud, or I can just type it in here in that diagram. So both is possible, and I'm happy with that initial design. In 3D, I see the same situation I had before for the impeller, but this time for the bowl diffuser with 0 thickness. And in order to save a bit of time, I just go quickly through the last 2 design steps, blade profile and edge design, by just using that last soft button, which allows to finish the design based on all default settings. Okay, now this is done. Again, I will quickly add some thickness to hub and shroud. Okay, I leave the shroud as it is here, but I change a bit the hub by splitting the curve again, moving the points, split it again, increase the degree, and adjust this point. in order to get what I want. I can also change the curve type to line segment and so on, and can define radii and stuff like that. But I'm going to save a bit of time and finish that. And again, I can apply fillet radii, but I don't let it run in 3D now, because the finishing of the design is something that is done in the cut kernel. All the surfaces that have been defined so far will be extended slightly in order to find intersection, and only then the fillet procedure will be started. Some Boolean operations will be done in order to get really watertight models. That would take a couple of seconds, what is the reason why I don't want to do that. But anyway, it would be the same as with the impeller. And finally, to prepare the model for CFD, I just add quickly inlet and outlet pipes just to extend the numerical region. And to this end, I just simply add a pipe with a certain length at the inlet without any vanes, and at the outlet. And here we are. Again, it should be an actual pipe with a certain length. At the outlet, it could be a bit longer, for instance, 150. And what I also have to do, I have to close the gap between the rotating and the stationary component just for simulation. And I'm going to do that by what we call the CFD setup. And here I can just introduce a kind of virtual domain, and it will just close that, and then the whole model is watertight, and I can go to the export panel and can choose Helix, for instance, choose the virtual flow domain for the export, choose all the components I want to include in the export, and then tell whether I want to export all necessary files or only the config files, which I'm going to do here, because otherwise it would generate STL files, which again would take a couple of seconds. And if I now choose the directory, for instance, the desktop, then I can just export it. It will be given here. And if I had the geometry also exported, one could immediately start with the simulation process in Helix. Okay, so having showed that, I'm at the end of my demo, and I would like to give back to Paolo.
Okay, thank you, Oliver.
I will now share my screen.
Let's have a look now how to set up the CFD model created in CFturbo using the Helix export functionality. So for this purpose, what we would like to do is to set up a sector model using mixing planes, run a steady state segregated solder via MRF approximation for the rotating impeller. And in terms of physical modeling, we're going to use a K omega SST turbulence model with curvature correction. Whereas for boundary condition, we will apply volumetric flow rate at the inlet equal to 210 cubic meters per hour. And the impeller is rotating at 2900 RPM, as defined in the CFD, CFturbo model earlier. And then the CFturbo to Helix interface will automatically define a sequence of mesh setup, solution, and post-processing actions in batch mode using the Python API available in Helix. So this means that the CFturbo to Helix interface will run our mesher, which is based on polyhedral self-grid generator, and then will also take into account surface and volume refinement, as well as near wall layers. Once a computational mesh is available, the setup phase will be done in terms of solution settings, material properties, turbulence models, boundary conditions, and output responses, which are quantities of interest, such as efficiency, power, and head of the pump that we want to measure. The next step, once we have a full CFD model in place, ready to go, is to run the segregated solver available in Helix. And we can run this in parallel on the workstation that you have available, or either this is also possible to run this in a HPC facility. So, for example, if you have your own cluster, or if your remote cluster, or if you want to access cloud resources, it's possible to fully exploit the open source nature of Helix by running in parallel at no extra license cost. And finally, once the solution is finished and we get a converged set of fields, we can do the post-processing using the graphical user interface available in Helix. So, for example, we can use the turbo post plots and graphs to extract the quantities of interest and to calculate the performance results. So now let's start with the CFturbo model, and this is the mixed flow pump that was created earlier. And the next step is to export the model to Helix. So for this specific purpose, we just click the export functionality here available in the CFturbo menu here, and we will basically select all the components available here. This includes the pipeline, which is the inlet pipe, the impeller, diffuser, and the outlet pipe. What we would like to run is the virtual domain, and we don't want to run the full 360, but because of the symmetry conditions and the periodicity, we run simply the periodic segment. In terms of settings, we just use the default settings for the geometry, and same applies to the mesh. So we just use the default scale factor. Scale factor is a scalar parameter which allows you to scale the cell size of the background mesh accordingly. So if you make this number higher, we will basically have a resulting mesh which a coarser cell size. On the contrary, if you reduce this number to a value less than 1, you will get a finer mesh. So once everything is set, you just click the export functionality here, and then this is the job is done for you. You just click this button, and this is what you get. This is the Helix configuration file and the geometry, okay, created by CFturbo, and the geometry is exported in STL format, right? So now the next step is to open the graphical user interface inside Helix. So in Helix, we will create a new case, and we can call it mixed pump and Q1 to 5, which is the speed. And then we run on 6 processors according to the capacity available in my local workstation, and then I click OK. The next step is to copy the configuration file created by CFturbo to the working directory of this case. So I just go back to the case folder here, and then I copy this file inside here, and here it is. So let's go back to Helix, and the next step is to run the CFturbo to Helix interface. So I go to macro library here, and then I right click here on the CFturbo to Helix interface, and this will run the script. So this is now running the interface, which basically completes the workflow as previously defined. So it starts from mesh, and as you can see now, it's populating the geometry and is creating the computational mesh. So This is meshing each individual component separately, and then once each individual component has been meshed correctly, the 4 different grids will be merged together in a single computational mesh, which will then be then treated for the setup phase in the next phase of the interface process. So since this process is going to take a few hours to complete, including the simulation run, I'm going to save you some time, and I have a case already open here, and here it is. So that's the geometry populated automatically by the CFturbo to Helix interface, and you can see here the 4 different ducts, and for each of them there are specific items, one for the hub, one for the shroud, then we have always an inflow, then outflow, and the periodics. And this is repeated for every single component. On top of that, for the impeller and the diffuser, we also have blades components. So these are individual surfaces which are defined here and separated from each other. And this is done in order to define specific mesh settings and boundary conditions, of course. The next thing that the interface does is to populate the mesh settings. So here we have different configuration, and we have one for diffuser, then another one for the impeller, and then for the 2 pipes. So if we take, for example, the impeller, we see here that we have a mesh algorithm. We have different algorithms available. The base mesh size with the ground mesh spacing, and we are talking about hexahedral cells here. And then for each surface, we define both surface and volumetric refinements. So here we can prescribe a target cell size and the near wall layers here to define the boundary layer. Just a comment here, the level, so the cell size here is a function of the dimension of the blades, and same applies to the base mesh here, the global spacing. So again, this is a function of the dimension of the geometry of the defined inside CFturbo. And this is repeated for every single component, and this is because the mesh is performed individually, and then finally all the different grids are merged all together. Once we have the mesh process completed, we can load the final mesh. So that's the final mesh here, and here you can see, for example, the mesh statistics here in this panel. So number of cells, number of points, phases, cell types, and so on. Right. Taking a closer look to the mesh here, we can see here the boundary layer on the inlet pipe, and then if we look at the impeller, this is what we get. Again, this is the boundary layer, and looking at the fillets, you can see that the mesher is automatically refined with a finer mesh spacing here on this area to account for the higher curvature. Okay, so that's the computational mesh, which is created inside the Helix. And then once you are done with the mesh, the CFturbo to Helix interface populates the setup tab. And as mentioned earlier, we would like to solve this problem starting with a segregated solver and running in steady state conditions. By the same token, it's also possible to run coupled solver, and there are 2 different types of solvers for the coupled. Option that we support is either pressure based or density based, and we will see later on how the coupled pressure based compares to the segregated one. And the next thing is to define materials. For materials, we have the water, so we define the density and the viscosity, and this is done automatically, and these are the water properties prescribed in the CFturbo. To model the rotation, we use a reference frame which prescribe a rotational speed equal to 2900 RPM. This is expressed in radians per second, and this is the reference frame that is defined here, and this is the axis of rotation. So this is rotating around positive Z here. Regarding the physical model, we use K omega SST runs with curvature correction. This is the one of the different turbulence models that are available in Helix. And the next thing is to define the boundary conditions, which are listed here underneath the external boundaries. And we start from the walls. So we define as no-slip stationary walls, smooth walls for all the hub and shrouds and the blades. So then the next thing we need to do for walls is to define the reference frame. So reference frame is global for stationary walls and is the rotating frame for the blades of the impeller. The next thing is to define the inflow volumetric flow rate. In this particular case, we use mass flow rate for the inlets, and then finally we have an outflow of where we prescribe the gauge pressure at the outlet here. And then we have mixing planes to connect all the different components to each other. So we have the outlet of the pipe one, which connects to the inlet of the impeller, and the outlet of impeller connecting to the diffuser, and so on. To account for the periodicity, we use periodic cyclic AMIs of rotational type. So here we define basically the axis of rotation for each of them. And these are working couples, as you can see here. To prescribe the rotation on the cells belonging to the impeller region, so we select inside sources and motion, the impeller, rotating impeller zone, and we define a source type MRF here, and the reference frame, rotating frame previously defined. We use the default numerical schemes. It's all second order accurate. Solver settings, we use a consistent mode, so actually a simplex variant of the segregated solver. And we want to run this for 500 iterations, which are enough to reach converged solution. And finally, we have monitoring function to account for the results, including, for example, the performance. Once we are all set with terms of this the setup, you run the solver, and finally we can take a look at the results. So, for example, we can monitor the convergence of the head here, and we can see how the solver has converged, and the same can be done for efficiency and power, and this is all possible to monitor here in this view tab. Looking at the fields, we can do, for example, a meridian plot where you can see here the total pressure moving in this meridional plane from the impeller to the diffuser. And same can be done if you want to use a blade-to-blade plot. And this is the same kind of information you get on a unwrap visualization plane. And then you can also visualize a turbo slice here. So, for example, this is done a 0.5 span-wise location between the hub and the shroud. And here all these vectors are the relative velocity vectors. So I can also change these, for example, 0.6, and see what you will get. And so getting closer to the shroud, if on the other and I just want to go closer to the hub, 0.25, for example, this is what we get. So these are for the plots. And then if we want to look at the graphs, or for example, if we want to look at things like blade loading to account for the pressure on the blade, so you take the turbo slice and you do a intersection with the blade surfaces. This is what you get in terms of total pressure. This is at mid span, and then here we get the pressure on the streamwise location. Similarly, we can have a hub to shroud moving in the span-wise location from the hub to the shroud, And finally, we have the inlet to outlet. And these are, again, showing the total pressure in the streamrise location. Now, if we want to repeat the same experiment and run the couple pressure-based, you can basically rerun the same process again. And now I'm going to show you the results which were obtained. So here you can see the results obtained in this table. And you can see that the results from the couple solver match quite well the ones obtained by the segregated solver. But in general, in Helix, we have two different types of solvers. We have segregated solvers, which can run both for incompressible and compressible flows, and couple solvers. And couple solvers are of two types, including pressure-based and density-based. But in general, couple solver exhibit a faster convergence versus segregated. So we are talking about 2 up to 5 times faster speed up and faster convergence. And if you look at the contour plots, then you can see that the segregated and the couple are pretty much similar. Yeah, the same applies here if we want to look at the blade to blade plots. And if we want to run the same process that we have seen so far for multiple operating points in order to calculate the performance curves, it's possible to use the Helix Python API to automate the process of setting up the case and rerun the case at different flow rates. So if you want to perform a flow rate sweep, this is what you can do. So you just take this the Helix Python API, and we run automatically the case again and again for multiple operating points. In this case, we have 5 points, and we can get the full curves automatically without manual change. So without even interacting with the GUI. And if we want to run a transient approach using a sliding mesh, we can define rotor-stator non-conformal interfaces and use a transient piezo solution algorithm, which runs basically with a time step for 2 degrees, and this actually rotates the impeller to perform a fully transient simulation. And the results are shown here in these animations and compares quite well to the steady state one. But in case you want to be to be time accurate, you can also use a transient approach, which is more expensive. So this basically concludes the demo for today.
Thank you very much, Paulo. Thank you, Oliver, as well for the demonstrations. That was very comprehensive. So we are now opening the space for questions. You can write your questions on the Q&A feature of the Zoho webinar tool. In the meantime, I have one question. So the current script that we have when we click on that Helix button on CFturbo, it imports the geometry from CFturbo and also generates the mesh automatically, right? But does it also generates or creates the setup for the CFD simulation, or that you should do afterwards? The mesh is generated.
Yeah, it definitely creates the setup as mentioned earlier. So it's a sequence of actions, including starting from mesh up all the way down to the post-processing, basically. And it's all automated. It's in a single script. Yeah.
So if I'm a customer and instead of an MRF approach, a steady state MRF approach or transient MRF approach, I want to create scripts or edit those scripts to match my existing workflow, that's totally possible because that's included in the Helix macro Python API, right? So I could literally customize this integration. Is that correct?
That's correct, exactly. In the case we shown today, we basically use the steady state MRF approach, but you can easily customize it and use the transient approach instead with the dynamic mesh motion, of course. Yeah.
Okay. Perfect. And a question for Oliver regarding CFturbo. Do you have in CFturbo capabilities to parameterize the geometry and then couple it with other optimization tools like Dakota, for example?
Yes, the possibility is there. To this end, we have a certain kind of interface which you can customize, and it will deliver an XML structure in which parameters are geometric parameters basically are defined. And in a batch run, you can call CFturbo with an attribute that is this XML file, and that will hold all the information that you want to change on your reference geometry together with export actions. So if you, for instance, want to run a Dakota optimized design process based on CFturbo and Helix, you would just tell, okay, the export should be all the necessary geometry data as well as the control information for Helix. And Dakota then would make change in that XML file. And every time CFturbo is called, those changes will be applied, a new export will be exported, and Helix could use it and run new CFD simulations, for instance.
Yeah, and I assume we could also expand this a little bit and use Helix output as input for the optimization process to parameterize CFturbo, right? So that would be really nice as well.
Yes. Yeah.
Great. We will launch the survey while we wait for questions, if any. Okay, so please, if you have some time to answer those questions, this will be very helpful for us. And we will wait for a couple of more minutes to see if we have any other questions. And we do have one question. Is it possible to mesh thin gaps without the cell count exploding? I think that's related to Helix mesh generator, right, Paolo?
Yeah, exactly. So we have a control to basically account for proximity refinement. So there is a way to define a tolerance below which basically you get an extra refinement. And the trick here is to find the minimum to optimize the settings to get the lowest possible number of cells without exploding in terms of cell count, of course. But it's definitely something we do it. For example, here in the it's quite typical, for example, in centrifugal pumps where you have small gaps between the different components to use this proximity refinement option.
Yeah. And I assume that the extrude mesh algorithm is way more efficient in this regard. Not efficient, but handles much better thin gaps than the standard algorithm, right?
Yeah, especially when you have to deal with boundary layer, of course, because you still want to grow near wall layers, and this is quite tricky, of course, with the standard algorithm that we have, but with the new algorithm that we have now in place, Helix is much easier.
Of course. Thank you, Paolo. So, if in case you have any other questions, you can always send us an email. If I'm not wrong, you can just reply to the webinar email that you received. And then if it's a question related to CFturbo, Oliver will address that question. If it's related to Helix or Aegis, we will address the question. So thank you everyone for attending today's webinar. I hope you found it informative and valuable as I did. And thank you, Oliver and Paolo, for your excellent presentations and demonstrations. And have a great day, everyone.
You too, Alessandro.
Thank you.
And thank you to everybody.
Thank you.
Thank you.
Okay. Bye-bye.
Bye-bye.